Okay, let's get started. Today we're going to talk about a little bit different subjects, namely fuzzing and symbolic execution. Previously, we mostly focusing on writing exploitations, but today we're going to focus on finding vulnerability. In fact, these are the techniques that you probably want to use during CTF and any other bug finding activity, right? Before we talk about this technical stuff, there's some diminished trivia. In-class CTF is scheduled on December 1st. Please find your teammate. You can work with maybe 3 to 4 people if you like, or if you like to just work solo, I think it's completely fine too. You have to submit your team challenge by November 27th. This basically will be your defense point for the TK CTF. If you submit your CTF early, we can provide some feedback. Or if you don't have any idea what to work on, you can talk to either TA or by myself, so we can discuss the potential challenges you can make as well. You can just come to the TA office hour and just talk about those as a team as well. Or anytime after the class as well. Again, so far, we focus on exploitations, meaning that we just give the proper locations of vulnerability. Right? Sometimes you can do cyclic 1000, you can get the locations, right? And we mostly focus on how to bypass the mitigations in that week. For example, given a Stack Overflow lab, we just provide a locations of the buffer overflow, and we enable some of the defenses like stack canary, and we are asking you to exploit those conditions, right? But today, we're going to focus on how to find those locations, particularly in the complex software, like web browser, for instance, right? There are multiple ways to approach this particular bug finding or bug auditing, starting with the source code. Particularly if you're looking for open source project like Linux or Chromes and whatnot. But in many cases, you have to deal with some proprietary software. So some of the product from Microsoft we don't have any access to. You probably want to start from the binary as well. We're going to talk about these two approaches by using fuzzing in today's lecture. In order to exploit a particular vulnerability, you first have to know the location of the bug. Either through auditing or by using tools and whatnot. Not only that, you have to find a condition that triggers those vulnerabilities. Sometimes we call reachability of those bug conditions. Given this very naive bugs that enables man copy of user's choice of LAN, you have to find a state that meet those conditions that trigger vulnerability. In this case, the magic value with particular concrete value, in this case that beef. Not only that, you should be able to spot the bug locations, in this case man copy. This is one of the vulnerability that we saw in real world. You guys can spot the bug. In fact, this is bug from the Apple. It was very popular at the time. Can you spot? This is a function that verify SSL, but it has a very naive bug. Anyone? What did you say? 9 9? What was the bug? Exactly, there is the extra go-to statement. What's the implication of this extra go-to? Exactly, line number 10 will be skipped and go to fail, in this case 14. Why is the problem? While we are returning in this fail loop, we expect that when we are processing or when we are executing this fail loop, we expect there is error conditions set. But unfortunately, when we are taking this line number 9, the error is not in fact error. In fact, it's actually success from this previous update function from SSL. In other words, without having any verifications, it actually returns true, meaning that there's no proper checking in SSL. You can think of all these HTTPS connections in Apple devices lively validate even if there's such a vulnerability. For example, some of the protocol errors in between, for instance. When it comes to static analysis, we actually test various tools. Like sometimes we use phone tools or GDB, or most of the time, the static analysis are preferred because just running the program, analyzing with the GDB is not that easy. But like static tool provide a lot of information and context when you're dealing with either binary, for instance. Like IDA or JIDRA are great examples that help you audit the binary itself. Unfortunately though, big programs like web browsers are not that easy. For example, if you're dealing with Windows kernel, probably not a good idea. Or macOS, for instance, because the amount of complexity behind the scenes are ridiculous. It's probably hard to deal with this complexity in your or decompile source code in JIDRA or IDA. So today we're going to talk about two dynamic approaches, unlike the static approaches that we discussed here, namely symbolic executions. It's an advanced version of static analysis per se, but we mostly talk about fuzzing in this lecture. Let me first talk about what is symbolic execution. Instead of concretely executing this particular functions, we're going to explore the state in symbolic manner. What we mean by this is that instead of saying the argument of the foo I1 contain a concrete value, for example like 1 or 0 and whatnot. So instead, we're going to say I potentially contain a range of value, what we say symbolic manner. In this case, entire range of integer, like to the int min to int max, for instance. Similarly for I2. Let's take a look in this foo function, what they're doing. If it get two arguments, namely I1 and I2 as an integer, and then assign to x and y, and then simply check the range of x. If x is bigger than 80, we're going to multiply 2 to the y. In this case, y simply contains the I2, and assign back to x. Right? And then we assign 0 value to y, and there's an extra if statement inside the first if statement. In this case, x is equal to 256, then we're going to return true. Otherwise, if x is less than 80, because we are doing integer arithmetic, and we're going to simply assign x and y to 0 value and simply return false. The purpose of the symbolic executor in this case to explore entire code paths. In this case, any state changes up to the return statement. And you can indirectly ask those questions like, in order to return true, in this case, what are the proper input range for I1 and I2 in symbolic manner? Or, in order to return false in this case, what is the proper integer range of I1 and I2 in symbolic execution? In order to evaluate those conditions, symbolic executor create a symbolic constraint, basically represent the state of the program at the moment. You can think of the PC executing each instructions one by one with a concrete value. Symbolic executor similarly execute instruction pointer one by one, but with the range of the path constraint. In this case, PC true basically represent my path constraint is met, so that I have to execute this one in the basically assignment of I1 and I2 to x and y in first block in the graph you're seeing in the right side. And then after executing this basic block, we're gonna execute a branch condition. In this case, whether x is bigger than 80 or not. If x is bigger than 80, we're gonna take the left side of the path constraint. Basically, you're taking the if statement in the basic block inside. If not, we're gonna take to the right branch in the graph, right? When we are executing, say, the right branch, say x is less than equal to 80, we couldn't execute the basic block inside the if, but we have to execute the else statement in this program. So in this case, we're going to add the additional path constraint. In this case, x is less than 80, less than equal to 80. Then we're going to assign 0 and 0 value to x and y. And then we're going to simply return false in this case. So if path constraint has been met, in this case, the left side of the basic block, then we're going to do simple arithmetic. In this case, x will be assigned with the y times 2, and y will be assigned with value 0. Right? In this case of the left side of the path constraint, x is bigger than 80. We're going to assign x with the new updated value, basically 2 times of y, and we're going to update the value of y. In this case, we simply assign 0 to the y. And then we're going to evaluate one more time because we're about to take the branch, right? In this case, x should be equal to 256 so that we can take the if branch inside. If that's the case, we're going to return true. Otherwise, we're going to return false. We're simply breaking out of this if statement and take the false statement at the end, which is the return statement of the false, right? Once you explore everything in symbolic manner, we can create a two path. In order to return true in these functions, we have a path constraint in the bottom. In order to return false, we're going to have a corresponding path constraint. For example, in order to return true, I should be bigger than 80, and I2 times 2 should be equal to 256. In order to return false, there are two possibilities. If I1 is less than or equal to 80, it simply return false. Or there's a little bit complicated path constraint. Either I1 is bigger than 80 and I times 2 should not be equal to 256. If we meet either one of those constraints, this entire function will return false as a result. The symbolic executor, after exploring these entire functions, provide two path constraints. The first one, they return true. Second one, they return false. You can think of this way: if there is a symbolic evaluation of, say, we simply check the existence of the buffer overflow. For every index use of the local variable will be expressed in this constraint manner, then we can check whether it can be met or not with the symbolic execution. So we're going to explore this one in the little bit different context of the fuzzing as well. Unfortunately though, it's really hard to manage this state in complex softwares like browser, or sometimes simple int functions, like for example square root. Given a integer range of I as an argument, how to express a return value. Sometimes it's extremely hard job, so that in many cases we are suffering from this state explosion. For example, given a symbolic input to the string compare, you can think of we have to compare every possible combinations of the string in this manner. So string compare might be implemented with simple for loop that compare each byte of the two arguments. But in fact, if one of the arguments is symbolically defined, then you have to compare indefinitely in the for loop. So in other words, the amount of path that you can explore through the symbolic execution is limited because of this complexity behind the scene. So we're going to introduce another approach, namely fuzzing, that can solve the state explosion problem in very interesting way. Anyone who heard about fuzzing? Okay. Anyone who tried? Anyone who actually find bugs in fuzzing? In fact, if you're looking for real-world vulnerability and you're tackling some of the program that you never played before, and fuzzing is a really good technique. According to, I'll say, Google's internal report, and in publicly known as known numbers are that the amount of vulnerability that fuzzer found way exceed or more than 10 times of entire of the bugs that unit testing can find in their history, the company's history, right? Fuzzing is a very popular and proven technique which is really good at finding real-world bugs. But in fact, the basic idea that we're going to talk about today, in fact, you can apply the exact same tool set to find the real-world bugs of the real-world software that you have in mind. The basic idea is pretty simple. We're going to execute the program with pseudo-random manner, right? Pick a random input, and you're going to run the program and see if it's crashing or not. If it crashes, great, you're lucky that you actually found the bugs. If not, we're going to mutate the input based on the past execution. If past execution doesn't reveal any new coverage, then we're going to do random mutations on the input. Or we can select some of the input corpus that we have and start randomly mutate those input before initiating a new fuzzing run in the program. And you simply keep repeating this process, right? Starting with the initial corpus, the initial setup, the input that you create, the fuzzer simply randomly mutate and start running the program and see if this new execution with the new input might hit another new coverage, new path in your program or not. If that's the case, then we're going to keep this input corpus and keep mutating. If not, meaning that it didn't reveal any crash, or it's just a redundant input that match with one of the input corpus that we have, we just ignore, right? And then keep repeating them. Hopefully, the good fuzzer can reveal many of the code paths and their corresponding input. One nice thing about this fuzzing approach is that whenever it hit bug, unlike Symbolic executor, you have an input. In fact, you can inject the input and you can crash the program with this concrete input pretty easily. So in other words, more pedantic way to say those is that we can get the reachability of these preconditions of exploitations are pretty freely given when we are doing this approach by using fuzzing. So what about this program? In order to say we like to find a constraint that hit this return statement, or return true. In order to let fuzzer to explore those conditions, we simply give a signal. For example, say we intentionally crashes this program to see that if this fuzzer can find a statement that return true, in this case on line number 10, and their corresponding state, we like to crash them. Otherwise, you keep just exploring all these paths by itself, so that say our goal is to find a constraint, the input state that hit this return statement, right? Return 1. What if we randomly pick the value of I1 and I2? How long does it take? Any guess? Is it hard to hit the conditions in line number 5 by using fuzzing? How big is the range of x? 2 to the 32. How difficult to hit this condition? Say you randomly pick 1. In fact, it's pretty easy. The near half of chance of picking one of those values. So in other words, by picking almost 50% of the chance you fall into the if statement, otherwise it goes to the else statement. In fact, we already discovered 2 paths. But how to trigger the line number 8? What should be the value of x after? What should be the value of y after? To meet the condition of x is equal to 256. Y should be 128. How difficult to hit this 128 value out of the integer space? In fact, this is just one value out of 2 to the 32. I'll say it's really impossible. You have to try almost 4 billion times, right? If you start randomly pick one. But interestingly, if you try a fuzzing approach, you might be surprised that it quickly finds in less than sub-second, it can find this particular conditions and start crashing. Okay, let me demonstrate how we can actually write the fuzzer harness that basically drive and test these particular functions in many different ways in this class, right? One of the popular approaches called Lec10 is another approach called AFL. The Lec10, basically you're going to create the fuzzing harness. You can think of the fuzzing harness as a driver of these functions. In fact, in order to utilize the Lec10, you have to provide a function name, LLVM fuzzer test1 input. What it does is pretty simple. Given a random data, then fuzzer will decide what data they're going to fuzz, and they're going to mutate and give the data, and then their corresponding size. And then we have another if statement that if size is too small, that doesn't even cover a 2 integer we like to test, we simply ignore. Otherwise, we're going to convert the first 4 bytes as an integer, another 4 bytes as an integer as a second argument. And then we're going to invoke a foo functions as a result. And after that, these entire fuzzers will run and start exploring every single path in the program. And whenever it hits the built-in trap, it will give you a report. Okay? Let me show you how we can actually encode this one by ourselves. I think we can just copy them. Let's copy this foo function. So this is a foo function that we like to invoke, right? And then we have to copy this fuzzing harness that drive the execution of the foo, right? So what it does, simply convert this random input from the fuzzer and start invoking these foo functions in here, right? Once you make this code, in fact, the CLang is just another compiler that based on LLVM. In fact, it provides many other toolsets that you can easily compile or enable this Lec10 as part of your project as well. So you can simply provide a sanitize option. Oh, so many. Sanitize. And then you can either just provide fuzzer. Is it fuzzer or fuzzing? Yeah, fuzzer. And then program. Because we like to enable some debugging information, we provide -g as an option. So I just compile. We got the a dot out. And you can execute this a dot out with the various argument. In this case, say whenever you execute, in fact, you actually execute very quickly already and start crashing this program. So if you make it small, say that in fact a dot out is the fuzzer that already integrated with the source code that we just wrote, and then you start with the corresponding random seed. And these are the, I'll say, whenever we crash, you're gonna have a call stack. In fact, many of them are just the boilerplate of the Lec10, but what's only interesting here is here, the foo function. You can see here. These are the functions that we wrote. The rest of them are provided from the library. The library, we accept this argument and randomly run, and it will invoke the foo functions as usual. Interestingly, it crashed already, and this is basic input. This is an input of base 64. I think they already recorded this crash. You can see this way. In fact, these are the input that program crash when they provide. You can see here, the first 4 argument is bigger than 80. Another argument, 128, which is the second condition of the program. If you see the second crash, in fact, it's pretty similar. First argument is bigger than the 80, but the second argument is consistently 128. In order to test this program, In fact, you can provide any crash as input to the program, and you will see the program crash as a result. Right? So it's a pretty easy to find bugs. In fact, think about how you apply this one to our challenge binary, and it immediately revealed the vulnerability in most of our challenge binary in this way as well. More original, I'll say, or more popular fuzzing approach is namely AFL. We're going to talk about this detail later, but let me quickly demonstrate how we can write the program for AFL as well. The AFL is designed to accept the program as it is, so that in order to test this full function, we have to write a program that just works. So in this case, what about we provide a main function to the program, see if we can apply AFL and see if AFL can find those vulnerability as well. So let's copy this guy. So in this case, we're gonna accept the user input. In this case, reading from the standard input, another 4-byte from the standard input, and just invoke foo, right? So in fact, you can compile this program with GCC in this way, right? In fact, in order to, and this program just run as you can expect it, right? But in order to compile with AFL, you can simply say, instead of GCC, you can say AFL GCC. Then AFL will instrument this code to inject extra code routine that we're going to discuss later today, so that it can be run by AFL, the fuzzer, together. Right? So after you compile, we have X. In fact, you can actually run X as it is, but you can run this, you can fuzz this program with AFL, right? In this case, we have to prepare some initial corpus. In this case, you can provide any type of input to the program, and fuzzer will mutate this one so that they can actually find the vulnerability accordingly. So let me create a new input, say just random AAA, and say a.txt. Then this is the initial corpus, nothing relevant to our program, but see if our fuzzer can mutate this program in a way that they can hit this vulnerability, right? So if you provide this input to program, in fact, nothing happen because we couldn't hit those conditions in this program. But what if we provide invoke this program under AFL fuzz? Then we have to provide two directory: the input directory that contain initial input corpus, the output directory output directory for bookkeeping of the AFL fuzzer. And then we simply provide the condition of the program. In this case, just execute X. So if you run this, AFL do some of the sanity check of the program and start finding bugs. And this is a typical console that you will see what type of mutation strategy is choosing, how fast it is, for instance. If you see this execution per second, it executes about 5,000 per second. So you can think of it pick 5,000 input and start executing 5,000 every second. In fact, it's a humongous amount of executions going on. Not only that, you can see the actual crashes keep increasing, but it consider only one unique crash. It means it already found the crash that hit this particular condition, right? So let's kill this one. If you navigate this output directory of AFL, you can see a bunch of data. The crash itself, the input that triggered the vulnerability, and some of the state, right? So these are the input that trigger the vulnerability. Can you spot the 4 bytes should be bigger than 180? But this one, because it can only accept the 1 byte and ignore the rest, in fact this work, right? Because we initialize I2 with the 0 value in our main program, and read only accept just 1 byte out of this input. Then if you provide this input to our X program will crash. So let's provide this, and program just crash, right? So in other words, given a random program, just running the fuzzer, and fuzzer will be able to resolve these complex routines in your program because of all the heuristics that we're going to talk about today as well. And then it will be able to find those vulnerabilities for you. In fact, when you're and then after you find those vulnerabilities, you can focus on writing exploitations after that, right? So what about crank me challenges? The crank me challenges is a binary. In this case, we cannot instrument the program for AFL fuzz. Instead, we're going to utilize another wrapper. In this case, cream_new will run the program and collect those, I'll say, coverage out of these executions and start enabling fuzzing as well. It's extremely slow, unlike instrumented version. Of course, because you have to emulate everything, but still work. Okay, let me show you how we can find bugs in crank me challenges by using AFL. So let's copy tutorial 1 crank me challenge. So this is just crank me challenge that we have, right? And then you can similar to what we did, let's delete this input output directory. So I'm gonna run so crank me challenge in this program. So it does the similar things, but you can see the execution per second is extremely low. It's about 1500 times per second. It's half of the speed, or one third of the speed of the native versions. But in fact, it actually found many vulnerabilities, many crashes. In fact, there's only one unique crash, so they save those input so that we can use those input for writing exploitations of the crank me challenge. Right. Similarly, if you see the output directory, you can see corresponding input. Right. In this case, it actually provides a right enough amount of A. You can think of the A was extended because we only provide X as original input. And then this A is got extended long enough that it starts triggering vulnerability in crank me challenge. Right? See if we can crash this one with the this one. Right? In this case, by providing this input, we can reproduce this crash by simply running, injecting those input to crank me challenge. Right? But what about how to find? What about we want to find a password instead of actual crash of the crank me challenge? Any idea how you proceed? Do you guys remember what was the password for the first crank me challenge? They're doing string comparison. Right? Then how to find them? By using fuzzing as approach. Any idea? Yeah, exactly. You can do the binary patching and say indicate that I like to crash with this condition. In this case, probably print key function. You can put trap, or you can do the binary patching of int3 or whatnot, and the program crash. Then you can say I found the password, right? Whenever you analyze the program binary, particularly in our CTF challenges, if you have a particular function that you want to explore, in fact, this is a pretty good idea, right? you like to encode some of the condition that you want to find, run the fuzzer, and see if fuzzer can find those type of input that you're looking for.
If you're not able to, binary patch, can we like check? Can we like make condition that if std out is not okay then?
You can create the wrapper to do all this job, but it is, I'll say, very tedious. I think you better just do binary patching. Okay. But do you think you can actually find by using this approach, either create new? In fact, it's actually not. There are many reasons behind this. Think about, we are actually instrumenting our own source code, not the library. In order to see anything interesting in the string compare routinely correct me challenges, fuzzer doesn't know anything about the second argument. Start really naively exploring those integer space, in this case data space, the array of the characters, which is almost impossible to randomly hit those particular string value. In fact, there are lots of heuristics that you can avoid. For example, you can say, you can dump the strings of the correct me, provide as a dictionary, then promote fuzzer to pick one of those values as part of the input, right? There are many heuristics that can bypass, but in this naive form of the fuzzing, in fact, fuzzer cannot find those particular conditions that trigger the password okay. So in these particular examples, we have to meet these two conditions. Integer 1, the first argument should be bigger than 80, which is pretty easy, right? But second argument is very problematic for the fuzzer. But as you can see here, fuzzer not only just fast, it can analyze those conditions and start finding those bugs as well. And we're going to talk about why it can find those bugs in their approach. Another important characteristic of the fuzzer is that if you want to fuzz a particular program that has very specific format of the input, you better create a input corpus that hopefully highlight or hit as many places possible in your program, so that whenever we do mutations inside the fuzzer, we should be able to exploit other paths. If you start with a naive dumb input like AAAA, probably not a good idea. Fuzzer can navigate those input space slowly, but it's not a good idea to start with. Particularly if you're developing a new software, you have a full test set, and you can start with the test set with the fuzzer, so the fuzzer can start mutate those input at the beginning. Think about your fuzzing browser. It's a pretty good idea to collect all the past vulnerability like HTML and JavaScript, so on not, and letting fuzzer to utilize those as our initial input. See if it can mutate and find a similar vulnerability as the past vulnerability, right? AFL is the most popular tool. You can either download. Most of the distribution now provide as nice packages, and there are a bunch of next versions of AFL as well, like AFL++ that I just demonstrated with the QEMU. But it's a pretty well engineered fuzzer outside, and Google engineer heavily rely on AFL, and many of academics also improve AFL significantly past 5 or 10 years. There are lots of interesting mutation strategies. Of course, given an integer, they're not just randomly mutate. There are lots of interesting input that we typically see like security vulnerability. Like -1 is a good number to test, like 80 or FF. These are the pretty interesting number for integers, and they do the simple bit flipping in each positions as well, or sometimes they do the random havoc, meaning they randomly pick the locations and start mutate or flip. And these are the typical approach of random mutations. But nowadays they have many more techniques, like see the argument of the second argument of the comparison, fuzzer statically analyze those conditions and start using them as part of the path constraints as well, right, when they're mutating the input. The key idea of the fuzzer is that after you run the program, and fuzzer can quickly evaluate whether this input is interesting or not. When I say interesting, is a new whenever this new mutated input let the program explore the new path that we never saw, we say interesting. If fuzzer just execute the same code path given a mutated input, we say it's not interesting, meaning that it's not worthwhile to keeping this input as part of the fuzzing process. But how to quickly evaluate this? Simple way is that you can collect all the instruction pointer during the executions. When you're done, you can compare two instruction pointer. So we have original input and we have past executions based on this original input. After we mutate, we also collect the entire instruction pointer, a sequence of instruction pointer, and start comparing. If they match, say, hey, this is what we already explored, it's not interesting. If we see the differences between them, we say it's interesting because it's now exploring a new path in the program. What's the problem of this approach? It's very expensive. You have to either collect every single instruction pointer during the execution. In fact, this demotivates the use of the fuzzer because the benefit of the fuzzer is performance. It's extremely fast. Any suggestion to improve this? Instead of collecting instruction pointer, what do you say? Exactly. You can just collect the instruction pointer of the branches, what we call basic blocks. So whenever you hit the basic block is a sequence of instructions. Whenever you start, you have to reach to the end. The rest of the instruction pointer is meaningless to collect because you're redundant, right? It's okay to collect the beginning instructions of the basic block, which is the target of any branches, right? In this case, we can collect a list of the basic block IP of the basic block, or we can map into the smaller version of them with the modular operation, right? If you say, I have this budget of 3 megabyte, I like to aggregate similar to the hash functions. We're gonna aggregate everything in this simple map, and when you're comparing, you can compare up to the amount of the size of the map, right? It drastically reduces the amount of computations of comparing. But what's the problem here? If function A and B are executed, and then think about B and A are executed, in terms of these notations, they're colliding each other. So in other words, there's no way we can distinguish these two different conditions. In fact, this happens all over the places, so that we like to at least distinguish the two different conditions, that we can jump from A to B or B to A. Particularly in the for loop like routine, is a very common problem. So they want to distinguish these two different conditions of the input space. So what they come up with is that we're going to keep track of the current IP of the basic block and the previous IP of the basic block. And then we're going to do very simple computations. Like we're going to simply shift in a way that whenever we jump from A to B and B to A, two different values are slightly different. Because we shifted to the previous block IP, the IP of the basic block. So if you XOR these two different values, you're going to have a slightly different version every time. And two different executions will be mapped into the two different places in the map. Any problem that you can see in this approach? Instruction pointer is a pretty good unique value that we can assign to the basic block because you uniquely identify them. But unfortunately, many of the basic blocks are nearby. If you do those XOR computation, many of them are just colliding each other. Some of the basic block in these two, the other basic block in the other places, as far as their offset is similar, they're colliding. So that the current approach that we are using in AFL and most of the fuzzers outside is simply assign a random value at compile time. So that each basic block will have at compile time a random value assigned, and they're going to use this random value as instruction point, so that we can uniquely identify during the execution. Anyone can see the problem of the random value? The last approach. Think about the for loop. This is oversensitive. Sometimes instruction point, if we collect a sequence of instruction pointer, it's very sensitive. If there is small changes, it says it's interesting. But think about for loop. Because of the way we distinguish the taking and not taking of the for loop, if you have increment of just 1 in the for loop, sometimes you want to ignore. Like in case of the string compare, you can say that if string is long enough, we just start ignoring those conditions in the map. In this case, they're gonna normalize the mapping before comparison. So in this case, if certain value is beyond the taking of the edge is beyond certain threshold, we start ignoring them. Then when we're comparing, at least we can have some of the buffer between those comparisons, right? So that we are not too sensitive, but sensitive enough to capture subtle differences of execution. But it has certain routines, very hotspot, for instance. Then one changes in the hotspot, we want to ignore. But if we see some of the changes in other part of the code, we say, hey, there's a new path that programmers start exploring, so we like to consider them as interesting. In order to avoid this redundant path, whenever we see the duplicated state, in this case, two mappings are colliding each other, we start ignoring. We are not putting back to the input corpus. But whenever we discover the difference, we say, this is interesting, so that we're going to mutate them in the next round as well. So simply put it back to the input corpus for the fuzzer. So how to create this mapping? So there are two approaches. Given a source code, as part of the compilations, we're going to instrument the code. Basically insert those specialized tracking of the basic block by the compiler. That's why we executed AFL GCC or clang with the corresponding instrumentation option. That basically do the code manipulations and put additional code snippet that keep track of this basic block at one time. Given a binary, we can do some of the tracings by using QEMU. In this case, QEMU translate this original code, and whenever they translate it to whatever IR in QEMU, they're gonna instrument, basically insert additional routine that keep track of these changes of basic block and start creating mapping for you, right? This is the actual code snippet of the QEMU. The ideas are pretty similar. It simply can keep track of the block address, that basically corresponding block address of the QEMU IR, and start updating the shared memory between QEMU and the target binary. And then after the execution, target binary contain a shared map between them, which we consider as a mapping structure for the fuzzing. If you instrument the code, you can see such a code snippet. In case of the foo, you can see AFL may be locked, and right before there is a random value. In this case, we assign F441 to RCX, and RCX represent a random value of the basic block the compiler assigned. And then by invoking AFL may be locked, it actually update the coverage map based on this random value. If you see the details of this assembly inside the maybe store, maybe AFL maybe lock, you can see this particular code snippet. What it does, simply XOR these two code locations in first XOR. The RCX originally contained the current location of the program, and perform XOR with a global variable, in this case previous locations. By XOR, we now have XOR version of two different values, and then we're gonna XOR again with the previous XOR version, meaning that we effectively assign the current location to the previous location. We simply update these global variables with these two simple instructions. And then we do the little bit of shifting, so that in next time we're gonna have we can distinguish the transition from A to B and B to A accordingly. And then we simply update this AFL area pointer, which is a share map between the fuzzers and fuzzing harness. If you run a fuzzer with, I'll say, JPEG or PNG parsers, image parsers, AFL work pretty well in terms of generating images, like magic. You can see various form of the images generated by AFL. In fact, various art associated with them. In fact, these are the new images that AFL can generate that potentially hit the new code paths in the program that AFL is fuzzing. Because fuzzing target in this case is Lec10 parser on a PNG parser or JPEG parser, and by creating corresponding input, indirectly AFL can create the original input that meet the conditions of this image parser, so that it ended up having all sorts of images that can trigger various conditions in the image parsers automatically. There are a bunch of other types of fuzzers, of course. The AFL and Deep AFL are available for source code instrumentation, but they're mostly expecting some binary format. But if you have some program that accept a very formalized input, then Radamsa is a pretty good fuzzer that aware of the syntax of the input as well. And there is a specialized target. There's a bunch of fuzzer that are specialized for particular target, like JavaScript and DOM element and rendering engines of web browser, for instance, right? And there are completely different approaches that combine symbolic execution and fuzzer at the same time. For example, when fuzzer couldn't find any bug, fuzzer quickly saturate if you start executing fuzzer for long times or day or months, right? At that moment, fuzzer decide the condition that symbolic executor might be able to find some, then indirectly invoke symbolic executor with the new the input that saturate the execution of the fuzzer, and symbolic executor can find those constraints, and hopefully it can create the new input that fuzzer can explore next. Right? This approach is called hybrid fuzzers, and Driller or QEMUs are pretty popular choice of today. In today's tutorial, we are asking you to write a fuzzing harness by using libfl and AFL. Also, if you're interested in, you can also do tutorial for symbolic executor. Particularly Angular and Clee are popular choice of symbolic executor. In fact, we also have tutorial for, I'll say, QSync. In this case, the hybrid fuzzer that combine fuzzers and symbolic executor as well. But these are optional, but we highly recommend that you explore this. And when you're auditing the real program or GTF, I think these are the pretty good tool that if you couldn't find any bugs in your program through auditing, right? You can think of one people in CTF team, just prepare for the fuzzing, and whenever you get the binary, just apply this one. Right? Then hopefully other people are navigating the binary, then fuzzer can also work on the side as well. You can download pretty much well-packaged Docker images in this tiny URL, or in fact you can find the corresponding resources in the web pages as well. Okay? Do you guys have any questions I can answer? Yes? Oh, that's a good question. There are several approaches in academia, which is one of the projects we propose as a research group. Is called native fuzzer, meaning that you can think of this way. Given a binary, you can patch the binary in systematic manner. For every block that we analyze, you can put it the crash intentionally. But if you can think of it, when you're running the binary, it's actually pretty quickly, right? But the problem of instrumentation here through those emulations is slow. But in fact, you can make it much faster near to the native performance because it's saturated. You can start with a think about all these basic block. We start with the like integer through is crash. Whenever you see the crash, you restore back, and at a certain point, the program we have all the input that enable reflip the crashing instructions in basic block, restore back to the original program. But the program just execute. Whenever you find a new input that trigger a new path that we never saw, then it start triggering the crashing instructions that we instrument in the basic block. Do you understand? So we start with the older basic block that we enable the crashing, but you have a bunch of input, you inject it, but you know kind of path that they're taking, so we flip back. At a certain point, because everything is saturated, you actually do the native performance. So even if you mutate something, as far as the program is not crashing, then say there is actually new code coverage that there's no new code coverage the program is executing. But whenever the program crash, it directly indicates that this one is for the new path. So that do the simple patching with the native binary, you can not only achieve native performance like the instrumentations, but one caveat of this approach is that unlike the edge coverage, this rely on the block-based coverage, so that we cannot distinguish the transition from A to B because of all the trick that we are doing. That in Patentically we say it's edge coverage because now we can distinguish transition from basic block A to B, B to A, with these simple manipulations of XOR of the previous locations and current location. But in this particular approach that we're tracking the instruction pointer of the basic block, so that we couldn't distinguish the transition of A to B, B to A. Good question. Any other questions I can answer? Thank you.